here's the idea. We are gonna use x-intercept of tangent line to approximate the zero. Okay, for instance, now in this graph, this function, let's pick a point as an initial value, say p0. This is your initial approximation to the real root p. Real root is unknown. Now to find the next approximation, you simply draw the tangent line at this point. So at this point, when x is p0, so you find the tangent line, right? So this is the tangent line. And this tangent line, the x-intercept of this tangent line is your next approximation. We call it p1 here. To find p2, repeat this process. Find the tangent line at p1, so which is this line, right? This line. And then find the x-intercept of this tangent line, and that would be your p2. So repeat this process to find the p3, which means, hey, you need to find the tangent line at when x is p2 and find the x-intercept. We will call that as p3. And you can see that p0, p1, p2, p3, the sequence generated by this method is, in this graph, is approaching the real roots p. So this is the geometrical interpretation of Newton's method. Algebraically, there are a couple different ways to introduce this Newton's method. The first one is using Taylor's theorem. So the Taylor's theorem with just first order approximation, this is it, and with its remainder term. So Taylor theorem gives us this result. And because p, we assume p is our root, right? P is root. So plug in p right here, okay? Plug in p, and plug in p. And with the substitution, we have this new expression. Okay, so simply just plug in p for x. And because f of p is 0, so this becomes 0. And now, again, p0, the initial value that we choose, is close to p, right? So when p is close to p0, or the same as saying p0 is close to p, this will be small because they're close, right? And with the square, this will be even smaller. Hopefully this makes sense, because if p minus p0 is small, just take one example. Say suppose p minus p0 is 0.1, and when you have 0.1 square, which is 0.01, so it will be smaller, because it's smaller, which is usually close to, not far away from 0. So this is close to 0, right? Okay, the previously it's an equation. Now because we're dropping this term, we say it's close to 0, so we change this to approximation, and this will be 0 and approximately equal to f p of 0 plus f prime p of 0 times p minus p 0, and the very last term is dropped. Okay, so that's the we get to this step now. Lastly, we just need to solve for p. Okay, let's solve for p. So when we solve for p from this approximation here, so it's equal to negative f of p0 is approximately equal to f prime of p0 p minus p sub 0, right? Now I'm gonna divide both sides by this term. So divide both sides by this term, f prime of p0, and we get to p minus p0, which is from here, right? And it's approximately equal to negative f of p0 divided by f prime of p0. And keep in mind, we want to solve for p, right? So at the end, p is equal to, approximately equal to, so move this to the other side, move that here, and that's what we have. And based on this we develop the Newton's method. So to Pn is equal to the previous approximation. So this is your previous approximation plus f of previous approximation, which is this guy, right? Divided by f prime of p sub n minus 1. So this is called the Newton's method, right? Now, with that, let's say this is p sub n minus 1, okay? And let's find the next approximation, which is p sub n. So let's think of those, okay? So we need to find the p sub n. And we are given that p sub n minus 1. So we want to find Pn based on previous approximation. So first of all, we need the equation of this tangent line. This is the tangent line right here. We need the equation so that we can find the x-intercept to get the p sub n. So let's do that. The equation is y minus f of p sub n minus 1. I'm using point slope form. What is this point? It will be p sub n minus 1 f of p sub n minus 1. So y minus its y equals the slope. The slope is the derivative at this point, right? This is the slope times x minus so the x0 in this case is the p sub n minus 1. The Pn is the x-intercept of this equation. So we just need to find the x-intercept. To find the x-intercept, we're gonna set this to 0, right? Set to 0. So when we set to 0, the above equation becomes f of p sub n minus 1 equals f prime sub p n minus 1 times x minus p n minus 1. Okay, and then we solve for x, which is the x-intercept, right? That's the x-intercept we want to solve. And this is the Newton's formula, right? We just derived that. So we derived the same formula in two ways. Some disadvantages about the Newton's method. First of all, you do see that the formula involves f prime. So sometimes this is difficult to find. That's why we have two new methods to be introduced in this section. So because this is one disadvantage. Secondly, if you can recall, we developed this result by assuming p is close to p0. So you do have to have a good initial approximation to make this method work. So usually that's our expectation. So we do have to have a good initial value p sub 0. The third one is this is not a root bracketing method. The consecutive approximation may not bracket the real roots. For instance, in this graph, the P2 and P1, this interval doesn't really contain the P. So this is not a good thing. Sometimes it may diverge, in other words. Now, this is Newton's method. Let's try to apply it to do some problem here. Algorithm. The book provides the algorithm. You will have to implement it and use it to solve some homework problems. Let's do some hand calculation. So this is the problem number 1. We consider cosine x minus x equals 0 as method to find P2. So according to Newton's method, my P1 is equal to P0 minus f of P0 divided by f prime of P0. And you do see that f prime is involved. So why don't we just find the f prime? So P0 is pi over 4 according to this formula. It's pi over 4 minus f of P0, which means cosine of P0, which is pi over 4. minus the x, which is pi over 4, divided by, here the bottom is f prime, so I need to use this function now. So my f prime is going to be negative sine of pi over 4 minus 1. After all the algebra, in numerical analysis, keep enough decimals. 8 decimals usually is a good number to use, okay? So please try to keep 8 decimals in your homework. So once we find the P1, let's find the P2. P2, this we are going to use this recursive formula, so it will be P1 minus F. For now, I'm gonna use my hand calculation. So the purpose is to demonstrate the whole process, right? So this is my P1 minus f of P1, which means cosine of my P1, and minus the pi over 4 on top, divided by the f prime of P1, which means negative sine of, not the pi over 4 anymore, but my P1, so 0.739 53613. 613, this is 13, minus 1. Okay, and I just used my calculator or Mathematica. This turns out to be 0.73908 Okay, so that's how I would solve my P1 and P2. Okay, let's use Mathematica program to find the roots accurate to 10 to the negative 5. So this is the accuracy needed. Now I did program my own Mathematica, implement this algorithm in Mathematica, and I use this accuracy tolerance 10 to the negative 5, and it turns out, so this is my output. This is my output. Okay, so this is my P1, P2, P3, and only 3 steps are needed for me to achieve this accuracy. And just for comparison purpose, if I run this using my fixed point algorithm, the fixed point program, this is my g of x, right? G of x, and at 7 steps, the fixed point method achieves the same accuracy, versus the Newton's method only use 3 steps. So Newton's method obviously is running faster when it comes to find the roots. 1 is equal to P0 minus f of P0 divided by f prime of P0. And my P0 is 1, so, and I just plug 1 in here. And my f of P0 is going to be 1 cubed plus 2 times 1 square minus 3 times 1 minus 1. The bottom is f prime of P0, which is f prime of 1. We need the f prime of x, right? So how about we just find it here? Minus 3. So we need to plug that in here. So 3 times 1 square plus 4 times 1 minus 3. And then the algebra turns out to be, the result is exactly 1.25. And P2 is equal to 1.25 minus f of 1.25, which means 1.25 cubed plus 2 times 1.25 square minus 3 times 1.25 minus 1 divided by 3 times 1.25 square plus 4 times 1.25 minus 3. And this is, well, this is approximately equal to 1.2009346. Again,